Good evening. Thanks for coming along this evening. Welcome to tonight's public debate called Brave New Brains. My name's Adrian and I'm the Director of the Neuroethics program for the Australian Research Council Centre of Excellence for Integrative Brain Function. It's so fantastic to see such a large and enthusiastic audience, particularly on a Monday night, so thanks a lot for coming along. Before we begin, I'd like to acknowledge the first and continuing custodians of the land on which we're gathered, the Wurundjeri and the Bunurong people of the Kulin Nation, and pay my respect to their elders past, present and future. The Brave New Brains event is an initiative of the ARC Centre of Excellence for Integrative Brain Function. The brain is the most complex structure in the universe, and the Centre of Excellence seeks to better understand how the brain interacts with the world by focusing on its structure and function. As we'll see tonight, these rapid advances in neuroscience raise some important ethical, social, legal and policy questions that we as a society need to grapple with. The Neuroethics program, in particular, explores many of the social and ethical and legal implications raised through our growing knowledge about the brain. Debates such as the one we're about to have this evening are an important part of coming to grips with the way in which emerging neurotechnologies can change society. And if you want to find out more about the Centre or the Neuroethics program, you can have a look at our website at brainfunction.edu.au. And while we're talking about social media, tonight we're going to be running questions through Twitter. So if you would like to ask some questions and engage with the panel, you can. Please use the hashtag BraveNewBrains, and we'll select some of the best questions to pose to the panel. So it is now my great pleasure to welcome the moderator for tonight's discussion, Lynne Malcolm. Many of you will know Lynne as the host of the ABC's All in the Mind program. You can hear All in the Mind on Radio National every Sunday evening at 5 p.m. or download it as a podcast. And we're really thrilled and honoured that Lynne's able to moderate tonight's event. So please join me in welcoming Lynne Malcolm.
Hello, lovely to be here. It's a fascinating discussion. Advances in neuroscience, computer engineering and artificial intelligence are opening a new world that holds promise and challenges for scientists, philosophers and ethicists. New technologies that connect brain activity to powerful computers have the potential to revolutionise medicine. Brain-computer interfaces, or BCIs, may restore sight, improve mobility for people with spinal injuries, prevent epileptic seizures, allow those who have lost the ability to communicate to converse again. Emotions, thoughts and behaviours may also be predicted, detected and altered by BCIs. The ability to decode and influence brain activity presents ethical questions for society. Who's responsible for the thoughts, intentions or actions decoded in a person's brain activity? Who's doing the thinking in these instances? Who has access to a patient's brain activity? Are BCIs a new threat to privacy and the freedom of thought? And is this just science fiction, or are these issues we really do need to consider before BCIs are further advanced? To try and answer some of these questions, we've brought together leading international and national scientists, engineers and philosophers to discuss the unique challenges posed by the brave new world of brains and computers. First up, we'll hear a short talk from Dr. Hannah Maslen about some cutting-edge developments in BCIs. Hannah is the Deputy Director of the Oxford Uehiro Centre for Practical Ethics at the University of Oxford, UK, and Research Fellow at New College and at the Oxford Martin School. She works on a wide range of topics in applied philosophy and ethics, from neuroethics to moral emotions and criminal justice. She's a principal investigator in the Horizon 2020 BrainCom project, which aims to advance the basic understanding of speech networks in the brain and to develop innovative BCIs to restore speech. Thank you, Dr. Maslen.
Thank you very much, Lynne, and thank you, Adrian, for the invitation here this evening. So my job in this first 10 minutes is just to give you a bit of an overview of some of the technologies that we're going to be talking about. So I'm going to give you some examples of some brain-computer interface devices and also tell you about some exciting developments in the project that I'm working on, which is aiming to develop neuroprosthetic technologies for speech that will potentially enable individuals who've lost the capacity to communicate completely because they're locked in or have ALS, for example, to speak again via neuroprosthetic devices. So this is the first example I want to show you. This is a woman called Jan Sherman who was diagnosed with spinocerebellar degeneration, in which the connections between her brain and muscles slowly deteriorate. So she doesn't have the control of her limbs. And in this case, she was implanted with two very small electrodes, square electrodes, into the motor cortex of her brain, into the areas that would normally control her right arm and right hand. And through a lot of training with the algorithm and the device, she was able to control a robotic limb by imagining moving her right arm and right hand. And the activity that is produced in the brain, even when imagining this movement, could be decoded and interpreted by the device to move this robotic arm. Just to show you just how integrated these kind of technologies can get, this is an example of a prosthetic arm that is directly connected into the bone and muscles of this gentleman here in Sweden. And so this is in some ways an indirect neural interface because it goes via the nerves in his muscles, but he's able to control this prosthetic arm, again, by imagining certain movements. So both those were in some ways invasive. This is an example of a brain-computer interface device that's non-invasive. So this is a brain-actuated wheelchair. And the individual who uses this wheelchair would have an EEG cap, as you can see, fitted on top of his scalp. And this covers a much larger area of the brain. The electrodes detect activity across the whole brain. And to control this wheelchair, the user has to engage in distinct mental tasks. So in order to direct the wheelchair to go right, the user would imagine circular movements of their arm or their leg, for example. And this would generate activity in a particular part of the brain that controls movement. In order to turn left, the user would engage in a very distinct kind of activity. So would engage, for example, in word association, thinking of words beginning with the letter A, for example. So this would generate activity in a distinct part of the brain. And the cap would be able to detect whether the activity was in this part of the brain or that part of the brain. And in order to go forwards, the user would actually engage in a state of rest, and this would move the wheelchair forwards. Interestingly, for this device, this isn't the full range of movements that it can do, because the wheelchair itself will filter the context, will perceive the environment in order to see if there are objects, or, for example, if there's a wall on the left or the right, so that if the user directs the wheelchair to go left and there's a wall to the left, it will curve around the wall and go smoothly rather than driving into the wall. So this is a really interesting example of shared control, which is going to be true for most brain-computer interface devices because the processing provides some of the direction that will produce the output. The final overview example I want to give you is another non-invasive device that can be used for communication by individuals who've lost the ability to communicate. And this is known as the P300 speller. So when a stimulus that is particularly salient to an individual is presented, the brain will produce a particular pattern of activity. This gets called sometimes the salience wave. And this can be detected in the parietal areas of the brain. And so this works by sequentially highlighting the rows of letters. So the person who wants to select a letter will focus on that letter. And when the column that includes that letter and then the row is highlighted, the salience wave will be detected because it will be produced in the brain. And the letter can then be identified by the classifier because it'll work out from the combination of rows and columns. So moving now to some particularly cutting-edge work that I've been involved in. We've got a project in Europe called BrainCom, and this involves scientists working right from nanomaterials, working with graphene, it's the thinnest material that we have, two-dimensional material, through to psychologists who are working on speech decoding, and then clinical colleagues as well who are working on translational areas of research. And this project is aiming to develop a complete device that will be implantable onto the surface of the cortex and will process and decode brain activity that is associated with producing speech. And this activity can then be externalized as synthetic speech, so an auditory version of the speech that is intended to be produced can be externalized. Now, how does this work? So the mechanism that's looking particularly promising involves the articulatory motor cortex. So this is the part of the brain that is responsible for moving the mouth, the tongue, the lips, the larynx, and so on to produce words. And it turns out that when individuals engage in what is called covert speech, so they really vividly imagine producing words, producing sounds, this produces similar activity in this area, the articulatory motor cortex, as would be produced if they were actually speaking, if they were overtly speaking these words. So the micro movements that are associated with syllables, so when I move my lips to make a plosive sound, this is associated with a particular acoustic properties. The movement is associated with the spectral features. So in recording activity from this area, the articulatory movements can be identified and then mapped onto the acoustic properties to finally be externalized as speech. So we've been working alongside the scientists on some of the philosophical and ethical issues around this technology. And probably you're already thinking of one of the first issues that we thought about, which is how to ensure users have sufficient control of what is externalized. I'm sure you all have thoughts that you think to yourself in your head. And if this device is picking up activity associated with covert speech, we want to make very, very sure that the device can distinguish between this kind of more active covert speech production, the vividly imagining, versus just fleeting thoughts that might occur to somebody using the device. So there are a number of issues around control, which I don't have time to go into in detail, one of which is this issue around the voluntariness of producing the output. There are also issues around control of the processes that will produce the particular words that are said, given that the processing will include significant portions of artificial intelligence, so machine learning that will both include models of what in a particular language is likely to be said, given the words that have come before, and also flexible algorithms that will adapt to the user's frequency of producing certain words. But in this case, unlike in natural speech or standard speech, there will be this contribution that the device makes to correct or predict the speech that will affect what is produced as an output. So we've been looking at that as one of the topics. There are also a range of issues, which Lynne mentioned some of just at the beginning. There are going to be concerns around privacy of this kind of brain data, especially if it corresponds to speech or thoughts that have linguistic structure, possibilities potentially for hacking these kinds of devices. There are also, in the cases of speech, going to be issues around discussing treatment or other significant decisions with users of the devices, especially if they're communicating entirely via a prosthesis. And finally, perhaps more speculatively, we might think about prospects beyond the therapeutic or assistive domain for these kinds of technologies, perhaps in military applications or enhancement applications where speech may be interpreted much more by a device. Perhaps you can imagine having the Shakespeare download or using some kind of translator to talk in another language via these kinds of devices, which raise all sorts of interesting questions about the authenticity of that output as soon as the contribution that the machine makes is really significant. So that's the overview that I wanted to give you in this first 10 minutes. Hopefully it's given you some good examples which we're going to be able to discuss as we proceed with the evening.
Thank you very much, Hannah. Please join me now in welcoming the other members of the panel. And so if each of you could come as I announce you. Professor Eric Racine is the Director of Pragmatic Health Ethics Research Unit, Montreal Institute for Clinical Research in Canada. His research aims to bring to the forefront the lived experience of ethically problematic situations by patients and stakeholders, and then to resolve them collaboratively through deliberative and evidence-informed processes. Professor Jeffrey Rosenfeld is ACOBE, is the Director of the Monash Institute of Medical Engineering, is an internationally recognised neurosurgeon and is the lead clinician in the Monash Vision Group. The MVG is developing bionic vision device to restore vision in blind individuals. This is an implanted wireless electrode interface with the brain, which is an example of brain-computer interface, example of a brain-computer interface device. He has an interest in the technical, clinical, and ethical aspects of brain-computer interfaces. He is a Fellow of the Australian Academy of Health and Medical Sciences and the Australian Academy of Technological Sciences and Engineering. Dr. Isabell Kiral-Kornek is an AI and life sciences researcher at IBM Research. Isabell received her diploma in electrical engineering from Leibniz University of Hanover in Germany, focusing on signal processing and radio frequency applications with a special interest in cochlear implants. She subsequently did a PhD in biomedical engineering at the University of Melbourne. As part of Bionic Vision Australia, her research was centred around finding novel stimulation strategies for retinal implant users. Isabell joined IBM in 2015, developing neural networks for biomedical applications and neural modelling. So we have a lot of expertise here. All right, so can you hear me? Is it on? Yep, great. Jeffrey, I wonder, first of all, can we start with the technology itself? What are brain-computer interfaces, and what's the range that's available?
Well, it's really brain-electronic computer. So brain to electronics to computer to maybe robotics, an effector of the brain information. So the interface can be outwards or inwards. It can be information that's taken out of the brain and joined onto a computer to do things, such as the example we just heard about speech recognition, or it can be information that's put into the brain from outside, such as vision, which is from a camera. So you can use sensory information to inform the brain where the brain may not be able to receive that information normally if it's blind or deaf or has sensory deficits, so on. So the interface can be at a superficial level on the surface of the scalp, as you saw in the slides, with electrodes placed on the scalp. So that's an electroencephalographic interface, or the electrodes can be placed directly on the brain, and that's beneath the dura and on the brain itself. So it's a more direct but invasive way of getting the interface. Or the ultimate is to actually place the electrodes in the brain itself. So that's the most invasive of all, but it's actually the most precise in terms of resolution of data, whether you're putting it in or taking it out, because you can actually theoretically record from little groups of neurons, even theoretically individual neurons, if you use nanoelectrodes, which are the tiniest. But if you connect to the neurons en masse, you would be having less resolution of the signal, and it would be more imprecise and more difficult to discern what the brain is really trying to tell you or tell itself. So that's the challenge, because we all would want to have a brain-machine interface that would just be on our scalp, so we wouldn't have to have our skull opened. But if you want to have the ultimate brain-machine interface or brain-computer interface, you actually have to connect the electronics directly to the brain, which is what we're doing with vision.
So what are the risks of that really invasive form?
Well, there are definitely risks, and infection is number one, because you're invading the surface of the brain. Number two is having a wired communication is not a recipe for success in the long term. Now, you'll see those patients that were on the screen before. The lady had these big towers on her head. Well, they're actually connected through her skull, through a plug in the skull, to those electrodes on her brain. So that's very invasive, and it's not going to be a long-term solution going forwards. We need wireless connectivity so that there aren't these wires coming out of the head which will increase the risk of infection. Also, when you stimulate the brain with electrodes, you're going to have a risk of epilepsy. So when you continually stimulate different parts of the brain, you'll get epilepsy eventually. So if the smaller the currents and the more precise the stimulation, the less the risk of the epilepsy. There's also the risk with the electrodes of them gradually failing over time. So the electrodes will incite an inflammatory reaction in the brain or around the brain, which could gradually degrade the signals and eventually lead to the failure of the device. So we have a challenge in getting these electrodes to work for years and years, particularly, or for a lifetime of the patient, particularly if we implant them into the brain. There's a challenge there. So they're the main issues.
So you're working on the bionic eye.
Yes.
And that will help to restore sight for people who are blind.
We hope.
You hope. Can you explain briefly how that works?
Well, what we're doing is to actually place the electrodes directly into the visual cortex of the brain. And these are people who've been blind for a number of years. They're the people we'll select. They're not congenitally blind, because if they've been blind from birth, we don't believe their cortex of the visual areas will be developed enough to receive the input. So it's acquired blindness, it's total blindness, and it's people who want to have it done, so they'll have to have it all explained to them and be willing to go through it as a guinea pig, as it were, because no one is having bionic vision implants at the moment. There's another group in Chicago who are working on it. But there are alternatives, and one of them is to have the electrodes placed in the retina of the eye, but there are many patients who will not be suitable for a retinal implant, such as patients with glaucoma, because they've lost the nerve connections to the brain. Patients that have had trauma, inflammation of the optic nerves, where those connections have been lost, the retinal implants will not work. So patients that have, say, cataracts or problems with the front of their eyes will be able to still have operations on their eyes to fix that. But there are patients who've lost the ability to take the visual information from the eye to the brain. That's where our device comes in. We're very, very optimistic that it will work, but obviously we haven't done it yet. We hopefully will get to do it next year.
Isabell, to turn to your work at IBM, you're part of a team developing a device to manage epilepsy. It's epilepsy prediction, isn't it? Tell us about that.
So we're not at IBM actually developing the device, we're working on the algorithms, which is important for IBM. What we're doing there is we're very much using the data of a electrode implant that is on the surface of the cortex that's been implanted for several years into 10 patients. And we're using artificial intelligence algorithms to try and distinguish the activity in the brain right before a seizure from the activity in the normal state. And so if we train an algorithm to distinguish between those two, then every time we recognize that activity is popping up that looks like last time a seizure was about to happen, we can, in theory, alert the patient that a seizure is likely to happen again.
So you can't be 100% accurate, though.
No.
No. And you're also using deep learning, like AI, in this as well. Are there ethical problems when you're working with AI?
I think there are several ethical problems or potential ethical problems. One that pops up a lot is that using artificial intelligence or deep learning in our case, you don't always know what exactly it is you're detecting or distinguishing between. So the moment we don't know what we base our prediction on, it's going to be really, it's going to potentially have regulatory issues associated with that. We're just taking a step in the blind and say, well, last time this kind of worked, but we don't actually know which part of the signal, which part of the brain is responsible for that. Excuse me, for that specific prediction. Another potential ethical problem, and that I guess goes into the direction of, for example, speech prediction, is often in AI the training set. So what's your population that you're training your algorithms on? And you can imagine that if you train a model to the English language, it won't work on all the other languages. So who are we designing those algorithms for? That's in the case of epilepsy prediction. In our case, that's irrelevant because all our models are patient-specific, so we know who we're training on. But more general, anytime it has to do with speech or even image recognition, we have to be really, really careful what we put in our training set.
So, Jeffrey, you were talking about the deep brain stimulation, and it's also been trialled in a range of conditions to control people's behaviour, like aggression, addiction, obesity. Should we be inserting electrodes into people's brains to control their behaviour?
Well, I haven't actually mentioned it. You just mentioned it. Because our electrodes are only 2.5 millimetres long, so they're just in the actual surface of the brain. They're not deep.
Okay.
So they're very, in a way, non-invasive compared with a deep electrode. So the deep electrodes are usually about a millimetre or so wide. They're used currently for Parkinson's disease mainly, and they're placed into what we call the basal ganglia, which are deep groups of nerve cells in the brain. And the one that's used mainly in Parkinson's is the subthalamic nucleus and also the globus pallidus and the thalamus itself. So they're all deep, very deep structures, and they're all small targets, so you have to use stereotactic techniques to place the electrodes accurately. So these techniques have been very effective at helping the movement disorder of Parkinson's disease, and now have been extended to other movement problems like Tourette syndrome. And we're starting to move now into psychosurgery, so surgery that alters behaviour. And the old days of lobotomy and leucotomy, then to leucotomy and lesioning in the brain are really over, because what's taken over from that is placing electrodes that stimulate the brain. They don't destroy any part of the brain, they actually just stimulate the brain with electric current. Now, there are ethical issues around this, because should we be using these again for psychosurgery? to help people with severe depression. That's under trial at the moment, and also for obsessive compulsive disorder. These are the two disorders that have been mainly trialled in the last few years using deep brain stimulation techniques. Also, it's being used for epilepsy as well to control severe intractable seizures. You can place the electrodes deep in the brain, in the thalamus particularly, and alter that. There have also been now trials of using these electrodes in parts of the brain to improve memory function in people with dementia, early dementia. So you can place the electrodes in, say, the fornix, which is a structure where memory pathways are, and you can, well, theoretically improve memory function, but it's not looking too good at the moment. It's not going to be a miracle cure for Alzheimer's, believe me. And then there's the application of deep brain stimulation for other behavioural issues like addiction to drugs, also morbid obesity and anorexia nervosa, severe anorexia, and even aggression. People are thinking about using it, and there have been a few reported cases for these particular conditions, particularly hypothalamic stimulation, which is the hypothalamus is the part of the brain that controls, well, it's intimately involved with all emotional function and aggression and hormonal balance and blood pressure, basic, control of vital functions. So obviously a very small, delicate target, but people are now starting to think about it for control of morbid obesity, which hasn't responded to anything else. So that gets into enormous ethical challenges. Obviously, when you're putting something invasive into the brain to solve a behavioural or a psychiatric issue, that becomes ethically incredibly challenging, particularly in view of the past history we've had, the very dark history of psychosurgery. And we're sort of starting to, and there were experiments many years ago to control aggression, very aggressive prisoners particularly, using psychosurgical techniques. And then we start to get into the question of political mind control, which also was one of the evils that sort of came out of the psychosurgery era. We don't need to get into that here, but you can see the enormous ethical challenges that are raised by people starting to explore these areas. And people are exploring them. It is happening.
Yes, so it can directly influence people's behaviour, and it may well be that people like the changes in behaviour and the changes in personality that
they may results. Do, but are they still the same person
That's
that they
right.
were before?
We're going to talk more about that. Eric, the insertion of DBS for debilitating neurodegenerative disorders like Parkinson's can cause significant strain on a relationship. It's estimated that around 50% of couples that undergo DBS end up in divorce or separation. Why do you think this is?
It's a good question. I'm not sure we have a definitive answer to this issue, but there are probably a couple of competing hypotheses. One of them is the treatment may not actually work as expected, and we know that the treatment is quite good, but not for everyone. A second explanation is that actually the treatment works, but the partners have trouble adjusting. So patients can basically become embedded in a sick role and identify with their condition. So if we, as we can do with DBS, change their tremors, for example, very quickly, part of their identity changes also abruptly. So that is something significant to adjust to and has caused a lot of strain to patients. And likewise, if the patient actually gets better and starts changing, then the person, the caregiver, can have problems adjusting to the kind of patient, not so much a patient anymore. So we've seen problems also of spouses having issues adjusting to a patient who now wants to become free again and regain different kinds of freedom and activities. So yeah, they're competing hypotheses, and I think maybe a third aspect could be that initially in the early days of deep brain stimulation, there was maybe not enough psychosocial support for the patients because we didn't really know about all these real-world outcomes of DBS. So I think nowadays, surgical teams, correct me if I'm wrong, are better supported and more well-rounded to foresee which patients and family units who could be struggling with those issues and be offered better psychosocial support.
So it becomes necessary to help patients weigh up the decision about whether to have these procedures.
Well, Parkinson's is such a terrible disease that most patients, if offered something that will improve their quality of life, will go for it. But if they understand the risks involved and weigh up the risks. But there are some side effects of DBS that have been found, and even of the medication itself before they get to DBS. And some of these patients develop hypersexuality. Some of them develop an intense interest in shopping. They just go, they're shopping mad. They go out and buy things. Some of them get addicted to gambling. They love gambling. So it's sort of the impulse control gets messed up by the DBS or by their medication. And so people are sort of grappling, the specialists involved are grappling with how to modify that. And it may be with improved electrode design and steering the current in the brain rather than having it blast out in all directions, may be a way of modifying these unwanted side effects of impulse, lack of impulse control. So you may be able to predict the patients that have these problems before the procedure is done as well. So these are the things that are currently occupying the minds of the neurosurgeons and neurologists involved.
Hannah, so how does this impact people's ability to carefully weigh up the costs and benefits of undergoing the procedure?
Well, I think it's true for any significant medical intervention that there are risks and benefits, and that it's really, really important that the patient is able to understand as far as possible, and if they don't understand that, then sort of changes things, but understand as far as possible what is likely to happen. I think with a lot of these more innovative interventions using DBS, it's sometimes really hard to predict what could happen. And so some of these changes associated with behavioral traits and other things that we might think of as associated with personality, for example, may not be predictable in advance. But I think one of the things that's particularly important to note relating to DBS, unlike lesioning interventions, is that it's to a large extent reversible, at least insofar as you can turn the stimulation off. You could even explant the device. You can certainly turn it off. So this gives us a really good opportunity for asking the patient how the intervention is affecting them when undergoing the stimulation, but also when the stimulation is paused, and also engaging their close family members or friends perhaps in discussion about how the treatment is affecting them. So I think that DBS is particularly interesting in this respect, because neurosurgery previously has not allowed this possibility of really sort of trying to track these potential changes and having a discussion with the patient about whether, all things considered, if there are some of these certainly unintended and perhaps unexpected side effects, whether they would, all things considered, want to continue with the treatment overall.
And there are other influences too that affect people's expectations. And Eric, I think you've conducted extensive research on the way these interventions are portrayed in the media. What did you find?
Well, in a few words, media coverage of deep brain stimulation and other stimulation techniques is really optimistic. And we can understand why, for the reasons being that there are few therapeutic options for many of those patients with severe neurodegenerative conditions, for example. But certainly, strikingly hopeful coverage, and a lot of miracle-like stories are depicted, probably sparked by the fact that DBS can really have, in some conditions, really like immediate effects. So it's really amazing. If you are interested, you can YouTube, some stories, and you'll see the dramatic effects of a DBS stimulator being turned on. So those kinds of testimonials and stories have a huge impact, potentially, on patients and families.
Mm. And that's a concern of yours too, isn't it, Isabell, in the expectations that are created in seizure prediction, for example?
Yeah, it's been both in working in the Bionic Eye project and also in the epilepsy space. People come and talk to us at public events, and they're very, very hopeful, and they read a story, and it very much portrays that that's something that will be available very soon. And it's both, I guess, very motivating to continue to work on it and to work harder and faster. But at the same time, I think we have to, as researchers, be really careful about how we tell those stories. I wouldn't want to put it on the media, because I think a lot of the stories we tell as researchers are trying to portray our research in the best light possible, especially to the media, so it's going to get published and it's going to get attention. I think we really have to take the responsibility and just ask ourselves, I don't know, if I had that condition and I read the story, would it be obvious to me that this is lots of patient trials away, lots of implementation, commercialization, and that there are all these steps in between before we get to a point where I can safely consume that device.
So onto the issue of who we are, authenticity. Hannah, does the melding of mind and machine, that question, what it is to be human?
Well, that's a very big question. Of course, with all these kinds of devices, users are going to have particular experiences of themselves using the devices. So there have been some studies looking at users' experiences of brain-computer interfaces, so prosthetic arms, for example, prosthetic limbs, and there is a range of experiences regarding the extent to which the user experiences that movement as actually theirs, or whether they feel like they're kind of observing something that is kind of related to what they're doing, but it's not really their device and their movement. I think particularly with speech, this is going to be really interesting, especially as we often kind of learn what we think through speaking. Sometimes we don't really know what we intend to say before we speak. Sometimes things come out better than we thought they might. Sometimes they come out worse. And so when using a device to communicate, this is going to, I think, really kind of push the limits of this question around kind of the authenticity of our using devices to engage with the world, especially as there will be this significant contribution from processing into the output that will use algorithms and language models. Sometimes we take our cue about what we think by hearing what we say, and so there's going to be real questions around whether the users experience that output really as kind of representing what they want to say, especially if they don't sort of know for sure in advance exactly what it is they're going to say. They just sort of start speaking and hear themselves speak, and the processing will have contributed to that output.
So Eric, does this resonate with you? Are we creating cyborgs as we've feared?
Well, I don't think we're there yet, to be honest. But I think, as Anna was saying, the experience of users, I think, is really diverse. I think some users are finding this extremely useful. They're seamlessly integrating this technology. Others feel differently about it. They may feel a little bit more like cyborgs, if I may use the word, but it's probably not exactly what they're experiencing. But I think we're seeing a range of, of perspectives, and I think we should be open to that and learn from these early clinical trials, and kind of think about their implication on people's identities. And I think a lot of those issues have been encountered with other non-neuro technologies. For example, in Montreal, I'm involved in work on the ethical and psychosocial aspects of the artificial pancreas, which is completely having to do really nothing with the brain here, but the issues are strikingly similar. Some people love this new device. They feel it's going to support them and it's going to be seamless integration, and others resist or have more concerns, and they feel like this will be something that disrupts their sense of self-control and their self-care and healthcare management. And I think we'll likely see the same with brain-computer interfaces. And I think learning from that will probably, open up our minds and eyes to different forms of realities that we're creating by these the new technologies and mixtures of machine and man, a human.
It also raises the question of responsibility. Do you take full responsibility when there's a combination of technology and a human self? What are your thoughts or fears around how we hold people responsible for their behaviours? Hannah?
Yeah, sure. So there are sort of a range of questions that we might ask around responsibility. The sort of simple ones are about whether you directly caused something, but then there are also questions about whether we should hold you responsible if, for example, you somehow caused some harm using your device. And I think there'll be a number of ways of thinking about this. So there might be clear cases where the device has just malfunctioned, and then there will be manufacturer liability. But there'll be more complex cases where the user, it requires skill to use these devices. Sure, you get used to using them, but there will be some shared control, for example, with the brain-actuated wheelchair I showed you, where it's perceiving the environment to combine with the commands that you're giving it. And so there's this element of kind of knowing how the device works. And so we might think about it as analogous to kind of complicated tool use, so that even if you're driving your car and there are, you have mostly have control over it, but if you knew that like your brakes were perhaps not completely sensitive, for example, and you ended up causing some damage, then we might still hold you responsible, even though you didn't have complete control over the dynamics of the car, because it's a device that you have learnt how to use, and that you're aware of its limitations. So I think, we shouldn't be too quick to assume that users of BCIs are going to be held responsible for harm caused by their devices. But I think we'll probably think about it in analogous ways, where there's this sort of control, shared control dimension, and it's similar to kind of complicated tool use, where you're using a tool that you should understand how it works.
Mm. Isabell, Hannah has talked about being able to decode people's speech from brain patterns. What other sort of personal information will it be possible to extract from people's brain activity? And, should we be concerned about that privacy issue?
I don't think we know yet. I don't think we know what's possible. I think there's a few factors that play into that, like where the electrodes are placed, for example. So you can imagine that the signal is much stronger in the brain than if we have an electrode cap that sits on the scalp. That's one issue. Then the processing is the next issue, and I think it's just not far enough to know where the limits are. Hannah said earlier, at the moment we're at least at the scalp level, we're at a point where we can distinguish whether someone thinks about moving their arm or spells something that's very far away from detecting if someone's lying or sharing very private thoughts, I think.
Jeffrey,
yes. Add to that, I agree with all that. But this field is moving incredibly rapidly, and it's outpacing our knowledge base in the general sense that the specialists know what's going on, and the scientists know what's going on, but it's happening incredibly rapidly. For instance, there's a group in the US who've been able to capture the memories of a mouse brain for a maze, getting through a maze to the food at the end of the maze, and they've captured the neural signals for that, and they put that into a small prosthetic device, which is then implanted into another rat's memory cortex, and that rat knows where to go in the maze straight away. So the rat has learned from that memory circuitry that's electronic now, but it's mimicking the original circuitry of the brain in the rat. It's now electronic. It's implanted electronically into the rat, the new rat. The rat now has the memory.
Wow.
So that's already happening. I'm not saying it's happening in a human, but it may be, we're moving in that direction. That's where things are going. And in fact, a company was set up in the US to develop a memory implant for a human. I think $100 million went into that company. So they're trying to develop it. I don't say they'll succeed anytime soon, but science is moving at a pace. Don't be surprised if in 10 years there is such a device.
And we're also only too aware of what Google and big tech companies are, listening into everything we do and say. I mean, the issue of hacking. Are we concerned about that, Eric?
Maybe. I think, however, some of these concerns shouldn't be specifically directed to brain-computer interfaces. I think we're learning with the events around Facebook, for example, and so on, that data is much richer than our categories often suggest. For example, that putting a label of something being brain data, I think could be a kind of an interesting but maybe not so useful kind of strategy. I think it's probably more important to look at the impact of data, to see at really what we're concerned about and how sensitive or not so sensitive the data are, before moving down the path of regulation and trying to come up with regulation that would be specific to brain data or brain-computer interfaces. Because I think increasingly we're seeing linkages between the behavioral, the psychological, the implicit cognitive biases that we hold that can be read by different kinds of interfaces. So I think the science is moving incredibly fast, and I think we should perhaps be mindful of the technologies, but really looking at what kind of context in which those technologies are going to be used and what kind of impact it's going to have.
The other area is, and we've only got a few minutes to go, but enhancement. These some companies are selling commercial, non-invasive brain-computer devices to monitor our health, but also to enhance our abilities. Are these things that we should be advocating or willing to use or even commercialise?
So there have been a lot of examples of consumer brain stimulation devices in the last 5 years or so. So this would involve sending a very low level of electricity through the skull to modulate brain activity. And these have been sold by companies for a whole range of purposes, actually. So gaming is a big one, but also for other sort of enhancement capacities, so around memory, perhaps mood, for example. And I think these kinds of devices, that the most important thing at the moment is to make sure that consumers aren't putting themselves in danger and are making decisions based on full information. So there's been a change in European regulation, actually, or there will be when the new medical devices regulation comes into effect, to include these kinds of brain stimulation devices within medical devices regulation. So even the ones that are sold for enhancement purposes, not therapeutic purposes, they'll be held to much stricter standards than they were previously. Previously, they weren't really regulated beyond, are they going to blow up or are they radioactive? And so there will be particular requirements both for the kind of limiting the amount of stimulation, placement of electrodes, providing information, particularly perhaps, stopping the device from being active more than once a day and so on. So I think sort of it's a big question about whether we should be encouraging people to use them, but certainly I think the first thing is to make sure that any devices people are using are doing what they say they do and not creating or posing risks that go beyond that necessary in order to do what they say they're going to do.
And they also have the ability to create an inequity in society, really, don't they? Some people may have access to enhancements because they've got money or they've got contacts, and others won't. There's a bit of a risk of inequity there, isn't there, Eric?
There could be, because obviously people won't have equal access to the technology, but I think we should be careful about having sweeping conclusions about this yet, because I think some of the uses could be highly beneficial in educational contexts. So maybe it will look as enhancement for some, it will be kind of treatment for others. And I think, that's a possibility. And then also, in terms of the efficacy of those devices, they may have like really different kinds of effects on different people, just like drugs have really different effects on different people. It may work for some, may not work for others. So I think we'll see probably a lot of complexity, and we'll have to be probably very sophisticated in thinking about whether a catch-all category such as enhancement will actually be equal to greater injustice. May actually be something that normalizes a bit like performance across individuals or brings more fairness, or it may not. I think it depends a bit on how they're used, how they work, and in which context they're used also.
We could go on, couldn't we? There are so many questions and issues, but I think it's now time to turn to you, the audience, for questions. If you'd like to direct your question to a specific panellist or generally, just let us know.
You have been discussing mainly the application of the machine-brain interface to pathological circumstances. And so certainly that's a very noble thing. I wonder if you are learning anything more about how people think and how people learn. And I'm asking this question more or less vaguely aware that the information age is changing the way in which people are thinking and learning.
Who'd like to answer that?
Well, there's a lot of neuroscience that can be done without invading the brain. There's a lot of neuroscience being done to understand how people learn and how the mind works. You don't necessarily have to put electrodes in the brain to do that, or even on the brain necessarily. But people have speculated that the human, through the cyborg concept, is changing its nature. The evolution of the human as a human may change over time to be not necessarily an enhanced human. It may be enhanced, but the computer is altering the way that we do learn, as you said, and the way that we do behave, and that when we connect ourselves to computers directly into the future or to the cloud, this may further alter the way humans act and behave, so that our evolution as pure humans may evolve into more of a combined human electronic interface. That's science fiction to a large degree at the moment, but that's what writers are speculating, and philosophers, and we have them here around me, they can comment, but that's where things are heading into the distant future. So hopefully that will sort of answer your question.
Okay, next question.
Hi. I'm just wondering whether any of your research could help people with Huntington's disease who have a slow but inevitable onset leading to a time when they're relatively young, when they can no longer communicate but can still think.
Hannah?
I don't think so. The work that I'm involved in isn't working on that, so I wouldn't be able to comment on developments in that area of medicine or technology.
I mean, there are lots of treatments that are being trialled for or developed for Huntington's, which range from brain transplants, neural transplants of embryonic neurons to replace the neurons that aren't working properly in the pallidum of the brain, or the putamen, sorry. Putamen's one of the centres for Huntington's. But also gene therapies are being looked at, and different electrode stimulation of the brain to try and slow down the process. But there are a whole lot of things going wrong in Huntington's in terms of movements and thoughts and speech, as you say. So it's not just the speech, it's a lot of the other things as well, and the memory. And so it's a very complex problem, but people are working on it. But there's no breakthrough at the moment as far as I know, but there are lots of things in the pipeline.
Thank you. I think we've got time for another couple. Mm-hmm.
Hello, this is a question for Professor Rosenfeld. You were speaking before about the nano electrodes. I was thinking as you increase or as you decrease the size and increase the resolution of what you're looking at, do you then require a larger network of electrodes to actually resolve useful information rather than just this neuron has communicated with this neuron? Are we looking at like a synaptic level or an individual neuron level, or?
Well, people are starting to think about and even doing experiments using nanoelectrodes in the brain. There's one group that actually inject the electrodes into the brain as a network that's been published. The network being that the electrodes are actually all joined together, but you inject them through the brain. It's not in humans yet. It won't be for a long time. But then there are ways of getting the nanoelectrodes into the brain through the circulation. So you might inject them into the circulation and they'll enter the brain. You can steer them with external magnetic currents, so you can place the nanoelectrodes where in the brain you want them to be, and the nanoelectrodes can then record and stimulate parts of the brain. They may be used to release drugs into the brain or change their molecular structure depending on external magnetic signals. These are things that are all being done experimentally at the moment to try and alter brain function. But in the future, it's thought, what's predicted, that we'll have enough electrodes in the brain to connect the brain externally, wirelessly to the cloud. That's the ultimate aim, to connect the brain directly to the cloud. It's not coming anytime soon, but that's a lot of people are working to try and achieve something like that, but at the moment it's at a very basic level. In fact, there was a recent paper that came out about a year ago where a group in Israel had placed nanoelectrodes in the brain of a beetle and altered the beetle's brain function by external magnetic currents. Obviously we're dealing with a very small brain, but it's getting going in neuroscience. People are thinking about this. I'm not doing it personally, but I'm keeping up with the trends in the literature. But the idea eventually is to have, you can't do it with individual microelectrodes to communicate with millions of neurons. And in fact, DARPA, the Defense Research Agency in the US, had a challenge where they would pay a lot of money for a group that could place 1 million or so electrodes in the brain and communicate with the neurons. I don't know whether anyone's actually achieved it yet, but that DARPA is wanting them to achieve it. So that actually has defense implications, but there we are.
Very interesting, thank you.
Yes.
We've got a question from Twitter. Given the rapid pace of technological development, how can the public stay informed and retain the ability to participate in ethical issues that may arise?
Well, by having forums like this, and by trying to make what we're talking about intelligible to the average person or the interested person who is not a neuroscientist. We must be able to speak in the language of the general public and allow them to be engaged in the debate. So it becomes a public debate, not actually a debate. We're having a general discussion at the moment, but it should become a debate, and the general public should be able to influence the way that the research develops, particularly when it affects human beings. And then we get more into the legislative side, and the politicians enter the equation, and it's very important that the general public enter it before the politicians do. And so that the general public as a whole have much more influence on it than individual politicians who may not necessarily be the best people to decide things.
Hi. So, my question is the problem with research is that if you don't do it, then someone else will. So, since we're talking about regulations and ethics, can anyone give me an example in the past where anything was successfully regulated throughout the world and it was successful? Because,
I'll give you one example. I'm sorry to hog the show, but the cochlear device is a brain-machine interface, but it goes into the cochlea, which is an extension of the brain. The cochlear device is now marketed internationally. It's an Australian invention, as it were. Yes, it was trialled initially with single electrodes in the US by House, but Graham Clark here in Melbourne developed the cochlear implant, which is now the best-selling cochlear device. And I have nothing to do with the Cochlear Company whatsoever, but it is the best-selling cochlear device in the world by far, because it is the best one on the market, and it's used worldwide. And it brings deaf people into a situation where they can hear again. It's a miracle device, and it's marketed worldwide. Is that a good example for you?
Yeah, I was asking, it's so difficult to regulate things like these. So, for example, I was asking for a successful example of a regulation that could actually stop some negative effects of a technology. Because you see, just like with genetics, there were some regulations in the US, but China did it. So,
you mean regulation to halt the pace of development? Is that what you're asking for?
Yeah.
We can't hear you down there, sorry.
The answer there would be exporting foreign medical aid under the guise of helping and going for a country where the same laws don't apply.
Are you talking about delivering these technologies into developing countries? Is that what you mean?
I'd be talking about how to find a legal framework that allows you to do whatever you want.
Well, we can't do whatever we want. Everything we do is, for instance, in these animal experiments I've been talking about, everything is controlled by ethics committees, and eventually it gets published, and if it's thought to be illegitimate or immoral or illegal, it will be stamped out. But it, you have to have a moral agency in the society, in a legal framework and an ethical framework that will allow this type of research to be done in an acceptable manner. But we can't hold up scientific progress totally. I mean, we can hold it up to a certain degree, but we have to hold it up to high ethical standards and let it proceed. And general society can be informed of that and should be informed of what's happening and be part of the decision making. as to, and that's why general members of the public are on ethics committees in hospitals and at universities to help the society at large inform the scientific brains around the table as to what is acceptable and what is not in terms of scientific research. But we're moving well away from brain-machine interface, but these legitimate concerns.
Yes, Eric.
And I think once the technology is available, people are free to use it or not. And I think the cochlear implant is a really good example of a successful technology, but some members of the deaf community fear that this is going to actually undermine the existence of their culture and their language. And I think there's been an evolving situation where it's been recognized that some people want to use it, and that's fine, and others don't want to use it, and that's also acceptable. So I think in a free, kind of liberal society, these things can happen, but we also need the technology to be there for people to then make decisions.
All right, I think, look, we've got time for one more question. This lady down the front here. Wait for the mic.
Thank you very much. It's been a very interesting symposium. I was just wondering how much of an issue is the concern about dual purpose research with computer-brain interface, and how much concern is there that it might impose on the research developments that you were talking about?
What do you mean by dual purpose? What's dual purpose?
So I think the question was around military use of these technologies, or perhaps more broadly kind of nefarious or unintended uses of technologies that were intended for either medicine or assistive functions. I think that there is, this is a topic that comes up a lot in relation to these devices. I'm certain that DARPA and other agencies are developing these kinds of technologies as well. I think they're probably not, wouldn't hide that thing. So I think the questions around whether dual use is actually a bad thing for a particular device has to be looked at before kind of assuming, and I'm not saying you were, but before assuming that dual purpose or dual use of devices is necessarily a bad thing. There can be important developments, of course, in military technologies that are good things. But these kinds of questions do come up in relation to all these devices. Actually, BrainCom, the principal investigator, project coordinator for that, has already had some interest from individuals around this technology. So I think, starting out with a very important focus on assistive technology, but already the kind of more speculative, more sci-fi potential applications are already in people's minds. If you could enable military personnel to be able to communicate silently, for example, then that would be something that could be hugely advantageous. I think some thought has also gone into brain-to-brain communication as well, which is again very sci-fi, but is something people are thinking seriously about. So, but I think it's not. The first step is to think about what applications of a technology should be avoided or prohibited, and where it might be a positive thing to engage with other agencies and companies to develop technologies beyond the kind of therapeutic applications.
Yes, and that really highlights the great importance in continuing to have discussions like this. Keep talking. So, look, thank you very much. Join me in thanking our terrific panellists, Dr. Hannah Maslen, Professor Eric Racine, Dr. Isabell Kiral-Kornek, and Professor Jeffrey Rosenfeld. Thank you very much.
While we're thanking people, please give a round of applause to Lynne Malcolm for a fantastic job leading us through the brave new world of brains and computers. And thank you all for coming along. It's been a really fascinating discussion. I hope you've all gotten something out of it. If there's any part of this that you missed or you want to watch again, I think we're recording and we'll be making it available on our website. So go and check that out. That's brainfunction.edu.au. And you can also go to the website if you want to find out any more work about what we're doing at the Centre of Excellence. You can also join our mailing list as well, so you can keep up to date about all the latest happenings and events that we're running. And I believe that Lynne Malcolm will also be doing a program on All in the Mind in the coming weeks around some brain-computer interfaces, so stay tuned for that as well. So thank you very much. And actually, I almost forgot a really important thank you, and that's to the team at the Centre for Integrative Brain Function for doing such a fantastic job at pulling this together. So that's Director Gary Egan, Merrin Morrison, Jessica Destart, and Glenn Papworth. Thank you.